Good evening, everyone. Let's just wait for 5 minutes so that everyone can join. So, today it is the last tutorial session for this course. I hope the earlier sessions were useful for you to understand the concepts and solve the problems. So, since we are completing this course, I would like to just recall the problems that we had done earlier so that it will give you a kind of revision. You can uh, see whatever, you can just recall what we did earlier in the earlier sessions. So, and also if you have any doubt in any of the tutorial session regarding any question, you can just ask me. This is the last opportunity for you to ask. After that, uh, I think you'll be having some exams and all. So, okay, let's start. I hope my screen is visible. So, yes, let's start with a problem that we did in our first tutorial session. So, if you remember, there we solved some of the differential equations from exact differential equations, some homogeneous linear differential equations, and all. So, let's start with first question. Show that a constant a can be found so that x plus y to the power a is an integrating factor. If you remember, integrating factor is a factor that helps us convert our non-exact differential equation to some exact differential equation, and the solution to the corresponding exact differential equation turns out to be same as that of our problem, which is initially non-exact. So x plus y to the power a is an integrating factor for 4x squared plus 2xy plus 6y dx plus 2x squared plus 9y plus 3x dy equals to 0. And hence, solve the equation. Let's mark this one as equation 1. So, first of all, let us see whether this equation first is exact or not. So, here we take mxy to be 4x squared plus 2xy plus 6y, and nxy is equal to 2x squared plus 9y plus 3x. So if you remember, this equation is exact only if del m by del y is equal to del n by del x. So here, derivative of m with respect to y is 2x plus 6, and that of n with respect to x is 4x plus 3. Clearly, these two are not equal. Therefore, equation first is not exact. Now, we need to show that such an A exists. That means if we can find A, so that this x plus y to the power A is an integrating factor, we are done. So, let A is A belonging to R is such that x plus y to the power a times mxy dx plus nxy dy equals to 0 is exact. That is, Del m bar by del y is equal to del n bar by del y, where m bar is just x plus y to the power a times mxy, and n bar is equal to x plus y to the power a times nxy. And now let us see. Now del m bar by del y is equal to, so we have x plus y to the power a as it is, del m by del y. And what is del m by del y? It is 2x plus 6. So this is basically x plus y to the power a 2x plus 6 plus a x plus y to the power a minus 1 times 4x square plus 2xy plus 6y. So this is, if you evaluate this properly, it will turn out to be x plus y to the power a minus 1. So then inside we'll have x plus y to the times 2x plus 6 plus a times 4x square plus 2xy plus 6y. And if you simplify it, you will get x plus y to the power a minus 1 times 2 2a plus 1x square plus 6a plus 1y plus 6x plus 2 1 plus a times xy. Similarly, del n bar by del x, just differentiating it as done for the case m bar, you'll get this is equal to x plus y to the power a minus 1 times 2x square a plus 2 plus 3y times 3a plus 1 plus 3a plus 1 times x plus 4xy. So now we have taken a such that the problem is the updated problem, this one. The equation hash is exact. That means del m by del y is equal to del n by del x. So in that case, we must have the same coefficients for x square, x, y, and xy. So from here, this implies we must have 2a plus 1 equals to a plus 2. 6a plus 1 is equal to 3a plus 1. 6 equals to 3a plus 1, and 2 times 1 plus a equals to 4. So in all the 4 cases, the value of a should be unique. Then only we can say that such an a exists. So here, this gives us a equals to 1. This gets cancelled out. So from here, we get a equals to again 1. This is 2. A equals to 1. This is 2 again. A equals to 1. Therefore, a equal to 1 will suffice our requirement. Hence, x plus y is an integrating factor. Now we know that the solution corresponding to the problem after multiplying it with the integrating factor is same as that of our given non-exact equation. So let us solve hash for a equals to 1. Solving hash for a equals to 1. Now since hash is an exact equation, this implies there exists some function f such that derivative of f with respect to x is m bar and derivative of f with respect to y is n. So this gives us f integrating equation 1 with respect to x, we get f is equal to, so what is m bar? M bar, so let's write f. X, let's expand m bar. So this is basically x plus 1, x plus y times 4x squared plus 2xy plus 6y, which is equal to, just simplifying it, you will get 4x cubed by plus 2x square y plus 6xy plus 4x square y plus 2xy square plus 6y square. Now integrating it with respect to x, we get fxy is equal to x power 4 plus plus 2x cubed y by 3 plus 3x square y plus 4x cubed y by 3. Okay, this is plus x square y square plus 6y square x plus some other function of y, because its derivative with respect to x will be 0. This is basically x to the power 4 plus 2x cubed y plus 3x square y plus x square y square plus 6y square x plus gy. Now differentiating this with respect to y, so we know that fy is n bar. So this implies n bar is equal to f, derivative of f with respect to y, which is, from here this is equal to 2x cubed plus 3x square plus 2x square y plus 12yx plus g dash y. Now we already know that n bar is equal to, if you just simplify in x plus 1, x plus y times 2x square plus 9y plus 3x, you will get 2x cubed plus 9xy plus 3x square plus 2x square y plus 9y square plus 3xy. This is equal to, from above equation we have, this is equal to 2x cubed plus 3x square plus 2x square y plus 12yx plus g dash y. So here 2x cubed gets cancelled out, 3x square gets cancelled out, 2x square y So this 9xy plus 3xy is basically 12xy. So we are left with g dash y is equal to 9y square, which gives us gy is equal to 3y cube. Therefore, what was our fxy? From here, fxy is equal to x power 4 plus 2x square x cube y plus 3x square y plus x square y square plus 6y square x plus gy, which is 3y cube. And hence, we know that our solution is given by fxy equals to c. So x power 4 plus 2x cube y plus 3x square y plus x square y square plus 6y square x plus 3y cube is equal to c, gives the solution of our problem. This is the general solution. General solution of hash and hence of star. First. So this is second, this is third, and this was in star, this was 1. So I hope the solution was, if you all remember, the solution. I hope the solution was fine with everyone, and we were able to recall what we did in first tube sheet. Next, if you remember, we did some qualitative properties of the solution. So, of some distinct solutions corresponding to second order differential equation. So let's just recall what a question from unit sheet 2, where we discussed that second order differential equation, for a second order differential equation, the two solutions are linearly dependent if and only if their Wronskian is 0. So we have show that two solutions y1 and y2 of the second order homogeneous linear differential equation ax y double dash plus bx y dash plus cxy equals to 0. Let's mark this one as 1, where a, b, and c are continuous functions. functions with a non-zero on interval AB are linearly dependent. So we were talking about the two solutions of this equation. So show that the two solutions y1 and y2 corresponding to the equation first are linearly dependent if and only if linearly dependent on AB, if and only if the Wronskian y1 y2 x is 0 for every x in closed interval. So here we need to show that the two solutions y1 and y2 are linearly dependent if and only if the Wronskian is 0. So we need to prove that if y1 and y2 are two linearly dependent solutions, then the Wronskian is 0. Conversely, we need to show that if the Wronskian is 0, then if the Wronskian of any two solutions is 0, then these solutions must be linearly dependent. So let us start with that y1 and y2 be two solutions of equation first. Suppose their Wronskian is 0. So what then in that case we need to prove that y1 and y2 are linearly dependent. So let's start with the claim y1 and y2 are linearly dependent. That means there exist some C1, C2 both non-zero such that C1y1 plus C2y2 is 0. So let x naught belonging to AB be arbitrary. Let x naught belongs to closed interval AB. Now this implies Wronskian y1 by 2 at x naught. This is equal to y1 x naught, y2 x naught, y1 dash x naught, y2 dash x naught, which is equal to y1 x naught. So we have this is equal to 0. y2 dash x naught minus y2 x naught times y1 dash x naught. Now let's mark this as second. Now consider the system of equations C1 y1 x naught plus C2 y2 x naught equals to 0. C1 y1 dash x naught plus C2 y2 dash x naught. equals to 0. So here y1 x naught, y2 x naught, y1 dash x naught, and y2 dash x naught are constants. The arbitrary variables are c1 and c2. Now let us consider uh, the system and the function fxy is equal to c1 y1x plus c2 y2x. Now if now since y1 and y2 are the solutions to our problem, then this fxy will be a solution to the given equation, whatever the value of c1 and c2 are. So this implies f is also a solution of given equation first. Let's mark this one as star. We can see that since the determinant here, since the determinant y1 x naught, y2 x naught, y1 dash x naught, y2 dash x naught is 0, in that case we know that this homogeneous system has a non-trivial solution. We all know that a homogeneous system of linear equations has a non-trivial solution only uh, if you remember, let me write it. This implies there exists c1 c2 not 0 solving star, because we know that ax equals to 0 has a non-trivial solution if determinant a is 0. Now since here this determinant is 0, therefore such c1 c2 exist, and corresponding to those c1 c2 we have constructed the function f. Now clearly f is also a solution because linear combination of two solutions is again a solution. This is a solution with f at x naught is equal to c1 y1 x naught plus c2 y2 x naught, which is equal to 0, and f dash x naught is equal to c1 y1 dash x naught plus c2 y2 dash x naught is 0 by equation star. Now this will give us that f is a trivial function, because if you remember we have a theorem which states that uh, if there exists some point x naught in the given domain such that uh, f x naught and f dash x naught are 0, then in that case f turns out to be trivially 0. Now if f is 0, this gives us c1 by 1 x, this is just x, plus c2 by 2x is 0 for every x. That means y1 and y2 are linearly dependent. Conversely, conversely, let y1 and y2 be linearly dependent solutions of equation, we have marked it as first equation 1. Now we need to show that their Wronskian is 0. Well, if they are linearly dependent, so there must exist, since y1 and y2 are linearly dependent, this implies there exists some c1, c2 when they are not 0 together, such that c1y1 plus c2y2 is equal to 0. This gives us c1y1 dash plus c2y2 dash is equal to 0. This implies Wronskian of y1, y2. Now, since these c1, c2 are non-zero solution, so this tuple c1, c2 is a non-trivial solution to this system star. So this implies the determinant y1, y2, y1 dash, y2 dash is 0. This gives us Wronskian is 0. So for every x, therefore, our Wronskian is 0. So I hope you all were able to understand the concept. I'll wait for 5 minutes. If you have any doubt, you can ask. Next, we will find some power series solutions. So next we have find the power series solution in the power of x minus 1 of the initial value problem x y double dash plus y dash plus 2y equals to 0. Y at 1 is 2, y dash at 1 is 2. Let's mark the system as equation first. Solution. So we will firstly convert this problem into standard form. So first this can now this is y double dash plus x dash, so plus y dash by x plus 2y by x is equal to 0. So clearly x equals to 1 is an ordinary point. So it is not giving us any singularity. Therefore, we can find a power series solution to problem 1 around 1. So this implies uh, x equals to 1 is a is an ordinary point. This implies there exists a solution. There exists a power series solution of first near x equals to 0. So we will start with assuming y to be some power series summation from 0 to infinity Cn x minus 1 to the power n. So this gives us y dash x is equal to summation n from 0 to infinity n Cn x minus 1 to the power n minus 1 and y double dash x is equal to summation n from, so we can write this as n from 1 to infinity, this is from 2 to infinity n minus 1 Cn x minus 1 to the power n minus 2. Now substituting star in equation first, we will get substituting star in first, we get summation n from 2 to infinity x n minus 1 Cn x minus 1 to the power n minus 2 plus summation n from 1 to infinity n Cn x minus 1 to the power n minus 1 plus 2 Cn, summation n from 0 to infinity Cn x minus 1 to the power n equals to 0. Now let's write this x as x minus 1 plus 1. So with that we will get summation n from 2 to infinity n minus 1 cn x minus 1 to the power n minus 1 plus summation n from 2 to infinity n minus 1 cn x minus 1 to the power n minus 2 plus rest of the terms being same n from 1 to infinity n cn x minus 1 to the power n minus 1 cn x minus 1 to the power n equals to 0. Now let's shift these n in such a way that we in all this summation we get x minus 1 to the power n same. So that we will get summation m from 1 to infinity m m plus 1 times cm plus 1 x minus 1 to the power n. So here we have basically substituted m equals to n minus 1. We have taken m to be n minus 1 in the first series. Then we have plus summation m from 0 to infinity m plus 1 m plus 2 c m plus 2 times x minus 1 to the power m. Here we have substituted taken m equals to n minus 2 plus summation m from 0 to infinity m plus 1 c m plus 1 x minus 1 to the power m plus 2 summation m from 0 to infinity. So here we already had n, so just taking m to be equal to n so that everything is uniform. So now let's take the extra part of the series starting from 0 separately, so that rest of the term we can club into one series from m equals to 1 to infinity. So this gives us 2c2 plus c1 naught plus summation m from 1 to infinity. Then we club the rest of the terms together, 2cm plus m plus 1 square times cm plus 1 plus m plus 1 m plus 2 times cm plus 2 whole multiplied by x minus 1 to the power m. This is equal to 0. Now comparing the coefficients of x minus 1 on both the sides. So since the constant term is 0 on right hand side, we get 2c0 plus c1 plus c2 equals to 0 and cm plus 2 is equal to minus 2cm minus m plus 1 square cm plus 1 by m plus 1 times m plus 2 for every m greater than equal to 1. Now let us use the initial condition to find these sum of the coefficients. So since yx was summation n from 0 to infinity cn x minus 1 to the power n, we had y at 1 is 1. So 1 equals to y at 1, which is just c naught, because rest of the terms will turn out to be 0. Therefore, we get c naught is equal to 1. Similarly, we had y dash x is equal to summation n from 1 to infinity n c n x minus 1 to the power n minus 1. This gives us 1, sorry, y dash 1 was, y dash 1 is 2. So from here we get 2 equals to y dash 1. So y dash at 1 will be just c1, because after that x minus 1 is 0, so rest of the terms will be 0. Therefore we get c1 equals to 2. So let's mark, we have marked equation 1, so let's mark this as equation 2, this as third, so this as fourth, and this one as fifth. So by fourth, fifth, and second, we get C2 is equal to minus 2. And then by third, we can find rest of the terms. So by third, we will get C3 is equal to, so we have to put m equals to 1. This is minus 2 C1. C1 is 2 minus m plus 1 would be 2. 2 square is 4 times Cm plus 1. That means C2. And what is C2? Minus 2 by m plus 1 is 2 and m plus 2 is 3. So this is minus 2c1. So this is 2 minus, taking out 2 common. So this, that would be 4 minus 2 by 3. That is 2 by 3. Similarly, we can find rest of the coefficients. C4 will turn out to be minus 1 by 6. And C5 will turn out to be 1 by 15, and so on. So therefore, we got the series solution. Yx is equal to 1 plus 2x minus 1 plus, sorry, minus 2. Minus 2x minus 1 square plus 2 by 3x minus 1 cube minus x minus 1 power 4 by 6, and so on. So this is our power series solution. I hope this solution was fine and you all could recall what we did in this tutorial class. If you remember, we had done similar problems. So I'll wait for 5 to 10 minutes. If you have any doubt, you can just ask. Next, we will find power series solution using Frobenius method. So we have question number fourth. Solve 2x square y double dash minus xy dash plus x minus 5y equals to 0 by Frobenius method. In some interval in 0 to r. Summation. Now we have y double dash minus y dash by 2x plus x minus 5 by x square y equals to 0. Clearly you can see that x equals to 0 is a regular singular point. Let's mark this as first. So the Frobenius method says that we can find the power series solution of the form, let yx equals to summation n from 0 to infinity cn x to the power n plus r. Then we will try to find this r and the coefficients cn. We assume that this c naught must be non-zero. Otherwise, there is no sense in writing the series. So we started from the point where the coefficient is non-zero. So this gives us y dash x is equal to summation n from 0 to infinity and y double dash x is equal to, so this sum is from, I can write it as n equals to 0. It will be n equals to 0. Summation n from 0 to infinity substituting star in 1 we get so we have just we have just putting the values of y dash and y double dash in the given equation. So this, now we need to make the powers uniform. So everywhere we would uh, so we'll try to make the powers in terms of n plus r. So just this series needs to be changed. Rest of the terms will be same. So I'll just copy it, copy, paste. And in this series, if I replace n by n plus 1, we'll get summation n from 1 to infinity cn plus 1 x to the power n plus r. This is equal to 0. Now, taking out the term corresponding to n equals to 0 from this series so that we can club rest of the things. From here we will get r times, so this is, so this is 2c naught r minus 1 x to the power r minus c naught r x to the power r minus 5c naught x to the power r plus summation n from 1 to infinity. Let's see. We have I'll just write it directly after simplification. You'll get it to be n plus r times 2n plus 2r minus 3 minus 5 times cn plus cn minus 1 x to the power n plus r equals to 0. So comparing the coefficients of x to the power m on both the sides, we get so since on the right hand side coefficient of x to the power r is 0, from there we get, and c naught is non-zero, we get 2 r minus 1 minus r minus 5 is equal to 0, or this is 2r square minus 2r minus r, so this is basically r 2r minus 3 minus 5 equals to 0, or I can write it directly. So this is a quadratic equation in r. This is 2r square minus 3r minus 5 equals to 0. So this gives us r is equal to 3 plus minus, the discriminant in this case will be 7 by 4. So this is 5 by 2 and minus 1. And the rest of the part will give us Cn is equal to Cn minus 1 by 5 minus n plus r 2n plus 2r minus 3. So let's see what happens when r equals to minus 1. So in this case, this is for every n greater than equal to 1. N equals to 0 anyways, that is c naught. For r equals to minus 1, we will get Cn is equal to 1 by 5 minus n minus 1 2n minus 5 for every n greater than equal to 1. Or if we simplify it, we will get this is Cn minus 1 n 7 minus 2 for every n greater than equals to 1. So this will give us C1 is equal to, you can just, these are just basic calculations, you can simply compute them. C1 equals to C0 by 5, C2 will turn out to be C1 by 6, which is basically C0 by 30, and so on. Therefore we get yx is equal to, taking out C0 common, and x to the power r outside, you'll get x to the power minus 1, this is 1 plus x by 5 plus x square by 30 and so on. Then let's see what happens when for the case r equals to 5 by 2. In this case, they will get Cn equals to Cn minus 1 by 5 minus n plus 5 by 2, 2n plus 5 minus 3. So this is basically minus Cn minus 1 by n 2n plus 7. This is just basic calculation. You can compute it yourself. And with that, you will get C1 equals to minus C0 by 9, C2 equals to minus C1 by 22, which is basically C0 by 198. C3 will turn out to be minus C0 by 7722 and so on. This gives us y2x is equal to, taking C0 and x to the power r common, we get this is equal to 1 minus x by 9 plus x square by 198 minus x cube by 7722 and so on. So our general solution is linear combination of y1 and y2. Therefore, yx is equal to c1 x to the power 5 by 2, 1 minus x by 9 plus x square by 198 minus x cube by 7722 and so on, plus c2 times x to the power minus 1, 1 plus x by 5 plus x square by 30 and so on. So this is our general solution. These questions have a lot of calculations. I have actually skipped a few steps in between. Those are basic calculations. I hope you can deduce these things yourself. So I gave you a rough idea how to solve such a problem. Now let's solve some Sturm Liouville type of problem. Question number 5. Find all eigenvalues and eigenfunctions of 4 e to the power minus x y dash plus 1 plus lambda e to the power minus x y equals to 0, along with the boundary conditions y0 equals to 0 equals to y1. Let's mark this as 1. So the eigenvalues are basically the value of all those lambdas such that so that the problem first has a non-trivial solution. So basically we need to find all those lambdas for what such that for them corresponding to those lambdas the equation first has a non-trivial solution, and those non-trivial solutions are called the eigenfunctions. So firstly, let us convert this problem into a standard Sturm Liouville type of problem. So we have 4 e to the power minus x y dash dash plus 1 plus lambda e to the power minus x y equals to 0. Now differentiating this first part using the product rule, we get to the power minus x y double dash plus, so this is basically minus, this will go minus 4 e to the power minus x y dash plus 1 plus lambda e to the power minus x y equals to 0. Taking e to the power minus x as common, we will get 4y double dash minus 4y dash plus 1 plus lambda y equals to 0. Now since we know that e to the power minus x is non-zero, we get 4y double dash minus 4y dash plus 1 plus lambda y equals to 0. Now this along with this we have the boundary conditions y at 0 equals to 0, which is equal to y at 1. Now this is a second order homogeneous linear differential equation with constant coefficients. We know how to solve such an equation. We start with an auxiliary equation, look for its roots, and using those roots we can find the solution. We know the standard way. So the auxiliary equation here is auxiliary equation is 4r square minus 4r plus 1 plus lambda equals to 0. Now this is a quadratic equation. From here we get r is equal to 4 plus minus under root 16 minus 16 times 1 plus lambda by 8. So this is basically 1 plus minus root minus lambda by 2. Now based on the sign of lambda, we have distinct roots. That means for lambda equals to 0 we will have repeated roots. For lambda positive we will have imaginary roots, and for lambda negative we'll have real and distinct roots. So let's look at case 1 when we have lambda equals to 0. Well, in that case r equals to 1 by 2 1 by 2, and this gives us yx is equal to c1 plus c2 x times e to the power x by 2. Now we are given some boundary conditions. We have 0 equals to y at 0. Y at 0 is c1 That gives us c1 is 0. This gives us yx is just c2x e to the power x by 2. Also we have 1 equals to y at 0. Sorry, y 0 equals to y at 1, which is c2e to the power 1 by 2. Now this implies that c2 is 0 because e to the power 1 by 2 is never 0, is non-zero. So this gives us y is a trivial solution. But the eigenvalues are those lambdas corresponding to which the solution is non-trivial. Therefore, lambda equals to 0 is not an eigenvalue. So let's move to case 2 when lambda is negative. So we can write lambda to be equals to minus k square for some k non-zero. Well, in that case, r is equal to 1 plus minus k by 2. So we have real and distinct roots. So this gives us yx is equal to c1. So this is c1 e to the power 1 plus k by 2x plus c2 e to the power 1 plus k by 2. Sorry, 1 minus. So this is 1 minus k by 2x. Now let's look at the boundary conditions. 0 is equal to y at 0. Now y at 0 is just c1 plus c2. So this gives us c2 equals to minus c1. This implies yx, taking out c1 common, is equal to c1 times e to the power 1 plus k by 2x minus e to the power 1 minus k by 2x. So that also we have another boundary condition. 0 equals to y at 1. So y at 1 is c1 e to the power 1 plus k by 2 minus e to the power 1 minus k by 2. So this will give us c1 is 0. Because if c1 is non-zero, in that case e to the power 1 plus k by 2 is equal to e to the power 1 minus k by 2. So this will give us e to the power k is 0, which is never possible. Because we know that e to the power x is always non-zero. So since C1 is 0, this will give us that C2 is 0, this will give us that Y is 0. Again, lambda is lambda negative will never serve us the eigenvalue. So we are left with the case third, where we have lambda positive. That is lambda equals to k square for some k not 0. So in this case, we will get r equals to 1 plus minus k iota by 2, which will give us yx is equal to e to the power x by 2 c1 cos k by 2x plus c2 sin kx by 2. Now let's look at the boundary conditions. We have 0 is equal to y at 0. So y at 0 is just c1 because sin 0 is 0. So this gives us that c1 is 0. This implies yx is just c2 e to the power x by 2 times sine kx by 2. Now we have another boundary condition. 0 is equal to y at 1. So y at 1 is c1 e to the power 1 by 2 sine k by 2. Now we want a non-trivial solution. For that we must have c2 non-zero. So c2 non-zero will imply that sine k by 2 was 0. So this implies for c2 non-zero, we must have sine k by 2 is equal to 0. And we know that sine x is 0 only for x equals to n pi. So in this case, k by 2 should be equal to n pi. So therefore, we get lambda is equal to k square, which is mm, it was k square for 4n square pi square. Since it depends on n, I'll write it as lambda n. So these lambda n's are eigen values and the corresponding solution. So I'll write it as phi n x, which is just a scalar multiple of e to the power x by 2 sine kx by 2. So k by 2 is n pi, so this is n pi x. These will be our eigen functions. I hope the solution was fine with everyone. If you have any doubt, please let me know. Next, we moved towards the partial differential equations where we have more than one independent variable. So we started with the reducing the problem into normal form and then solving it further. We solved some wave equations, heat equations, if you remember. So I'll just recall a problem to reduce the a normal partial differential equation into its normal form, and then we will find solution using it. After that, we'll see if we can try some of the heat equation or wave equation problem, some initial value problem. Okay, so let's move to the next question. Question number 6. Reduce the partial differential equation uxx minus 4uxy plus 4uyy equals to 0. Let's number this as 1 into a normal form. And find the general solution. So in case of ordinary differential equations, a general solution had arbitrary constants, and in the case of partial differential equations, a general solution will have arbitrary functions. Find the general solution. So if we compare uh, this equation 1 with the standard second order partial differential equation, let me write that. The standard partial differential equation. So comparing first with the standard second order second order linear partial differential equation, AUXX plus BUXY plus CUYY plus DUX plus EUY plus FU plus G equals to 0, we get A equals to 1, B equals to minus 4, C equals to 4, and B square minus 4AC is equal to 16 minus 16 minus, so this is 4 0. We know that this gives us that our problem is that our partial differential equation is parabolic. And our characteristic curve is given by characteristic curve dy by dx is equal to minus b plus minus 0 by 2a. So this is minus 2. So from here we get, integrating it, we will get y plus 2x is equal to 0. So in this case, we will take some function zeta xy is equal to 2x plus y, and eta xy is equal to x. Now we can see that the Jacobian of zeta and eta is equal to determinant 2, 1, 1, 0. This is basically minus 1, which is non-zero. Therefore, such a substitution can be done. So this substitution is well defined. So now we will convert our problem from ux, uy, uxx, uyy to a problem where we have partial derivatives of u with respect to zeta and eta. So we have ux is equal to, now we'll differentiate u with respect to zeta, and we'll be basically applying the chain rule, del u by del zeta by del x. So this is 2. Similarly, plus u eta. So this will give us uxx is equal to 4u zeta zeta plus 4u zeta eta plus u eta eta. And then we will get u xy u and u xy is equal to, so this is 2u zeta zeta, derivative of zeta with respect to y, plus u zeta eta, and derivative of eta with respect to y is 0, so I'll write it directly 0, plus u eta zeta, again the rest of the plus 0. So this is uxy is equal to 2u zeta zeta plus u eta zeta. Similarly, we have uy is equal to u zeta plus u eta times del eta by del y, which is again 0. Uyy is equal to u zeta zeta, zeta with respect to y is 1 plus u zeta eta times del eta by del y, which is 0. So basically this is just u zeta zeta. So substituting these in equation first, we get by first we get 0 is equal to uxx minus u 4 times uxy plus 4 times uyy is equal to, so the uxx is 4u zeta zeta plus 4u zeta eta plus u eta eta minus 8u zeta zeta minus 4u eta zeta plus 4u zeta zeta. So this plus this gives us 8u zeta zeta. This gets cancelled out by with this term, and this directly cancels out. We are left with just u eta eta equals to 0. Therefore, del by del eta of del u by del eta is equal to 0. Now, if I define v is equal to del u by del eta, this gives us del u by del eta is 0. That means v is constant with respect to eta. This gives us v is some function of zeta only. That means del u by del eta is a function of zeta. Now integrating both the sides with respect to eta, we get u zeta eta is equal to eta times f of zeta plus some function of zeta. So basically, now replacing back to xy, we get uxy is equal to, so this eta was just y, just x. So this is x f of x plus 2y plus g of x plus 2y, where f and g are some arbitrary function that will depend basically on some boundary condition or initial conditions. So this gives us our general solution. I hope this solution was fine with everyone. If you remember, we already did this problem in earlier class. Next, we will solve an initial value and initial boundary value problem. So there we will have some initial conditions as well as boundary conditions for a partial differential equation. So let's move to next question, question number 6. Find the solution of the following initial boundary value problem utt minus c square uxx is equal to 0 for every x belonging to closed interval 0 to L, t positive and L is some constant positive. Along with the boundary conditions, u0t equals to 0 is equal to ut at L comma t, and some initial condition, that means at time t equals to 0 we have u0 equals to a sine pi x by L, and utx at 0 is equal to 0. So we'll be basically using the method of separation of variable, and I know we have done such problems so many times. I would like you to try this first. Start with taking ux t equals to xx tt, then reduce the two differential equations, and two differential equations, one in x, one in t, and there will be some parameter, some eigenvalue lambda, and corresponding to lambda n equals to, in this case you will get lambda n equals to minus n square pi square by L square. So I would like you to come till reach till this point where you can reduce that for lambda n equals to minus n pi by L whole square. The problem will have a non-trivial solution. So again you will have to solve a Sturm-Liouville kind of problem. So I'll wait for 5 minutes and I would like you to try this yourself. Reach at least till this point, lambda n equals to minus n square pi square by L square. So I hope you must have got that for lambda n equals to minus n pi by L square, we have xn x is equal to cn sine n pi by Lx, and corresponding to this lambda n, if we solve the equation corresponding to variable t and using the condition utx, using the initial condition utx at 0, that gives us t dash 0 is 0, you must have got that T is equal to some constant kn times cos n pi by L t. We have c also, no? C n pi by L t. So this will give us that unxt, which is, I'll write it as an sine n pi by Lx cos cn n pi by Lt is a non-trivial solution of equation. So let's mark the system as 1 of 1, and hence by the principle of superposition we get uxt is equal to summation n from 0 to infinity an. So this is from n equals to 1 to infinity sine n pi by Lx cos c n pi by L t. So then we will use the initial condition ux0 equals to a sine pi by L. This implies a sine pi x by L is equal to ux0 is equal to summation n from 1 to infinity an. So this is sine n pi x by L. Since cos 0 is 1, we have cos, we are left with just an sine n pi x by L. So from here we know we can evaluate an is equal to integration 0 to L a sine pi x by L sine n pi x by L dx by 0 to L sine square pi x by L dx n pi x by L. So these are basic integration. We know that this numerator will turn out to be 0 for every n not equals to 1, and for n equals to 1 this is just a sine square pi x by L. So this is a n is 0 for every n not equal to 1, and a is equal to a times 0 to L sine square pi x by L dx. In fact, the denominator will also be sine square n pi x by, sorry, since n is 1, so this is just pi x by L dx. So this gets cancelled out. This is equal to a. Therefore, our solution uxt is just a sine pi x by L cos c pi p by L. So this is our solution. So we'll have to stop till here only. I hope this course was useful for you people. I had tried my best to give all the explanation. And if you have any doubt, you are free to contact me. You can ask doubts regarding any problem in this session or earlier sessions. Even if you have some conceptual doubts, you can ask. So, with this, I would like to say all the best for exam and for future. I hope you will be able to see the beauty of mathematics and end up doing some research or going for further studies in mathematics. I hope you go for that. Okay, then. Thank you so much.